The topic for my presentation is high-fidelity interface and virtual environment for surgical training. My name is Heng. I am from the Department of Computer Science and Engineering at the Chinese University of Hong Kong. This video is recorded on 29 December 2019 at CUHK. So why are we interested in doing research for surgical simulations? So let's just look at the current dilemmas in surgical training. One of the best way to train a surgeon trainee is using cadaver. However, there's always limited supply, and also there's no dynamic conditions can be learned. And we can also train on animal. However, the anatomical structures for an animal is very different from human, and also there are no other complications that can be trained. And the worst case would be to train on patients because it can harm patients, and also many of the procedure is non-repeatable. So one solution is to use VR to create virtual environments to deliver surgical trainings. The advantages of virtual surgery includes configurable and repeatable training. With integrated software and hardware, we can construct very realistic virtual environments to provide support for different kinds of surgical training. In the long run, it can improve patient safety. However, there are quite a lot of technologies involved in building a virtual environment for surgical simulations. This includes medical image processing, data fusions and visualizations, soft tissue modeling and deformations, as well as haptic feedbacks to simulate the sense of touch during the surgical procedures. Also, we need to integrate all the above technologies in a very realistic virtual environments, and also go through a lot of testing and also systematic evaluations. So this is the framework for a typical virtual surgery training system. We can divide the environment into two components, the software parts and also the hardware parts. In the software, which is about the constructing the virtual environments, one key component is digital anatomy that involves geometric processing, realistic rendering, and parameter estimations. Another component is medical physics simulations that includes solid mechanics, fluid mechanics, as well as fluid structures interactions. For the hardware component, we need to simulate all sorts of surgical instruments as well as the haptics rendering. This is the outline of my presentations. I will go over some of the ongoing research in related key technologies, and also I will introduce some of the surgical simulation systems that our center have developed over the years. So in terms of the related key technologies that include medical image processing, deformable soft tissue modeling, haptic rendering, and realistic rendering of surgical scenarios. So let's take a look at medical image analysis first. In our work, we have dealt with ultrasound, CT, MR, in fact, all sorts of medical image modalities, including videos, even digital pathology. So a typical task in medical image analysis is semantic segmentations, which requires to draw the boundary of the anatomical structures. We have developed a 3D deep learning based framework. Generally, if we do a segmentation task with deep learning, we will build an end-to-end learning architectures, and every voxels would contribute to the gradients. Look at these figures. A segmentation network normally have several downsampling layers to gradually abstract these features and several upscaling layers to gradually fulfill the resolutions of the figure map and make pixel-wise predictions. The problem is that when the models go deeper, we would encounter training difficulties. For example, one typical issue is called gradient vanishing, which means the early layers in the network cannot be efficiently trained in a deep network. To solve this problem, we propose to also connect the early layers to upsampling layers and also use it to make predictions. In this way, during backpropagation process, the gradient can not only flow back from the very end of the model, it can also arrive these early layers by these shortcut connections. so that the entire model is more tightly supervised, and we call this method as 3D deep supervision mechanisms. Here are the results of using our 3D deep supervision networks on the application of diverse segmentations. The red control is the predictions by the deep learning networks, and then the green controls are the ground truth outlined by human experts. This network can handle large shape variations, limited contrast with nearby tissues, as well as tumors cases. And to validate the generalization capability of our proposed method, we replicate it onto a completely different data set, which is hard segmentation on MRI image. On this task, we also achieve state-of-the-art performance on the public benchmark dataset. After this work, we have extended our 3D deep learning segmentations to a set of variants. For network architectures, we propose 3D residue network, 3D dense network. We also propose 2D, 3D hybrid network, and region proposal-based network for reducing computation workload of the 3D model. And this network has been applied to a wide application scenarios, for example, liver, brain, spine, heart. And this segmentation result can be easily used in clinical treatment and surgical planning. So here is the some of the examples of our work on applying AI for medical image analysis. Include ultrasound image processing, fundus image processing, colonoscopy videos, as well as dermoscopy imagings. In a typical surgery, normally there will be blood. So blood vessels modeling and bleeding simulation is a common component. We use smooth particle hydrodynamics for these bleeding simulations, and we also develop blood vessels modeling based on glove and provide geometric modeling of the blood vessels network. Other components is soft tissue modeling and deformations. The earlier works typically will involve simpler mesh beam models. We also do multi-layer soft tissue modeling in order to provide more realistic deformations outcomes when the multi-layers of tissues are being involved during the surgical process. More recent work has been using the finite elements methods for simulating soft tissue deformations. So most medical simulation require interactively and realistically simulating the mechanical response of human organs under complex interactions. And then the interactions include tooth-tissue interactions as well as tissue-tissue interactions. So to develop a realistic mechanical response, we adopt an embedded deformable model. The advantage is that it can preserve volume and also allow smooth interpolations. So our deformable soft tissue modeling includes first step is the embedding hexahedral generations that it can automatically generate embedding hexahedral. And then we also adapt PET screen coordinates-based interpolations. The advantage is to achieve smoother interpolations and volume conservations. And then finally, to handle complex frictional context mechanics, we also solve the boundary conditions for embedded deformable models. Here show an example of a work on visual haptic simulation for interactive cutting under complex boundary conditions. For the geometrical modeling, we need to preserve consistencies between cutting plane and splitting trajectory and achieve volume visualizations. For the physically based modeling, we need to separate the computations of physically based modeling with geometrical modeling, which can effectively avoid the numerical instability and complexity issues. So we propose a hybrid geometrical models reconstruction method. We also propose a hybrid geometrical model update method for topological modifications. And in terms of rendering, during the simulation, the irregular measures and staircase will inevitably be generated during medical image reconstructions that will seriously impact the rendering performance and visual possibility. So we combine the complementary facet normal field and vertex normal field for filtering in order to detect the edge features for measures. And we also employ edge and barycenter constraint Laplace transformation for mesh moving. Then the advantages is that we can preserve important geometrical features and achieve volume visual conservations. The pictures show some of the smooth and optimizations of the 3D model for multi-branches blood vessels. Another work is about high-quality centerline abstractions of vasculatures mesh surface. It's quite common that we need to construct vascular structures such as in vascular intervention procedures. So in here, we adopt the steps that includes mesh segmentations, rotational symmetry exit, and principal component analysis. By doing so, we facilitate discrete geometric processing based on cylindrical shape assumptions. And then by doing so, we can achieve much better vasculature mesh surface segmentations based on this cylindrical shaped clustering. And here the figure shows the abstraction of vasculature mesh centerline with complex topology and geometric structures. And smokes and also freight are also some common phenomena in surgeries. So we need to show some details in this kind of simulations. However, there are some issues, for example, like the numerical dissipation in smoke simulations. This is because the vertical structures under grip resolutions are hard to capture and resulting in smooth simulation without ample details. Another issues in liquid simulation is the tensile instability, and the incomplete kernel support at surface causes inhomogeneous particles distributions and thus affects the numerical instabilities. So to overcome these problems, we introduce smooth particle hydrodynamics turbulence model for local particles computations and synthesize the long small-scale vertical structures under the grip resolutions. And by analyzing and processing of the fluid particle support domain, all particles can satisfy the complete kernel support. And we also introduce the particle distribution adjustment mechanisms to preserve thin features and realize the liquid simulation with rich feed details. For example, like the smoke simulations as well as the liquid simulation shown in the two pictures. So next, I'm going to introduce some of the surgical simulation systems that our center have developed. The first one is ultrasound-guided biopsy simulations. In an ultrasound-guided biopsy process, the surgeon need to insert a biopsy needle passing through some organs in order to extract tissues of tumors in order to make a diagnosis. So this is in fact quite a dangerous process and also require lots of training. So let's take a look at a video showing this setup. So, excuse me. In this work, we try to develop virtual reality simulators to facilitate training of ultrasound-guided biopsy. Biopsy is a process of taking a sample of tissue from organs, and this really need excellent hand-eye coordinations. We need to align the ultrasound transducers together with the biopsy needle on the same plate. In these two hand device, they are both haptic feedbacks can be provided. One hand is to simulate the transducers, and the other hand is to simulate the biopsy needles. In terms of data pre-processing, we have to acquire multiple ultrasound volumes, and then we need to stitch the acquired ultrasound volume into one complete comprehensive volumes. So the research involved is to do registrations of multi-ultrasound volumes. We adopt a 3D shift approach to carry out these tests. Later on, we also do ultrasound CT data registrations. That's because in CT can provide a lot anatomical details in the simulations. So then when the data has been pre-processed, we can, in the actual simulations, we can simulate periodic respiratory movements. We can align the transducers on the dominant, and then based on the location of the transducer, corresponding ultrasound slide imagings can be generated. And then the needle overlay can also be inserted into these visualizations of the deformed ultrasound volumes. So this is the system framework. It includes the CT volume processing, ultrasound data processing, and there will be needle servers to handle all the biopsy needles, including the rendering, the collision detections. There's a translution servers to deal with the ultrasounds, transducers, and that also includes collision detections. And then finally, there will be visualizations to handle the final output that includes volume rendering, to show the needle overlay, to show the shadow overlay, and or to show all the deformations as well. So in these figures, in this setup, we also can see that the force during this process is simulated, and we can observe that there are some peaks during this needle insertion process. It is at the puncture of the skin, the puncture of the muscle, as well as the puncture of the liver capsules. So that the user can in fact experience different force feedbacks, sensations during the surgical simulations. And then later on, we develop a series game for learning ultrasound-guided needle placement skills. And in the series game settings, we can dynamic generate different training cases, and so that we can control the case difficulties, and we can construct scenes with different building blocks. For example, the normal, that means that the needle can pass through without causing much problems. But for the vitus box, then the needle have to be stay away, otherwise damage can be caused. So this is a games setting so that we can have different levels of difficulties. And then for that, we will construct scenes and the corresponding ultrasound image based on the case settings. This system, the ultrasound-guided biopsy system, if it have been developed, and we have developed the systems to hospitals, and we invite surgeons or radiologists who use this kind of procedures in their clinical practice to try on our systems. And based on their feedbacks, we have go through several generations of improvements and eventually become a very useful and practical system for training these particular procedures. The second system that I would like to introduce is about vascular and interventional radiology simulators. So vascular and interventional radiology is a kind of image-guided and minimally invasive therapeutic procedures, normally through a tiny pinhole punctures under the visual controls of medical equipment. Mainly is to treat vascular-related diseases. So the image guidance in such a procedures includes X-ray fluoroscopy, computer tomography, angiography, and magnetic resonance angiographies. And in our work, we try to construct a virtual reality-based platform for learning the related anatomy and also training related procedures. Here is the system chart for such as simulators. So we need to construct in the segmentations. The input is CTA or MRI data. We need to do vascular modeling that includes centerline abstractions and so on. And then the second component is the catalyzation simulations. The third component is the embolization simulations, and also the angiography simulations. So let's, in these vascular simulations, we mainly focus on constructing the vascular network. So in vascular interventional radiology simulator, here are some of the key components: the blood vessel modeling, the catheter and guide wire modeling, X-ray fluoroscopy simulations, collision detections, and then finally is to integrate all the components into one nicely integrated systems. So this picture shows the vascular network constructions. So the geometrical modeling includes the bifurcation modeling, trifurcation modeling, as well as all sorts of tabular modeling. This picture shows the visualization results of the blood vessels abstracted. And we also need to carry out a lot of testing and evaluations and for comparisons with realistic physical simulation as well as simulated simulations. So the video show a demo of the constructed systems. So here the users can perform simulated vascular and interventional radiology in a very safe environment that will cause no harm to the patients. This is the pictures, both all the components are integrated and developed at our centers. We can see that the user can manipulate by pulling, twisting, and turning of these catheters to advance the catheters to the desired locations. So we need to simulate all the related components in such a system. For example, like the injection of contrast agents to highlight the relevant blood vessels in the navigation path. And we can see that this is quite a difficult task. It typically will require a long training for a surgeon or radiologist to acquire this kind of skills. And with this kind of virtual environments, we can shorten the required training times in a repeatable and configurable manners, so that we can construct different cases. The user can try different cases until they have very confident, until they are very confident about that kind of procedures. Another type of simulator that I would like to introduce is about the focus here. The main focus here is about haptic rendering. This is a mandibular angle reductions surgical simulators. In the mandibular angle reductions, mainly is for the remodel of the facial control. Is quite efficient and quite popular procedures. There are two basic strategies involved. One is the linear mandibular angle of stepstomy, and also the other is the smooth ridges or sharp edges, the smoothing of these ridges or sharp edges. And then the tools being used are the rotating blur or the saws. And the picture here show the remove protruding parts in this kind of procedures. So then the difficult parts for this particular simulator is about haptic simulations, because it's involve multi-point contacts of a high-speed rotating blur. So the basic idea to compute the blurring force is that first we need to check for multi-point contacts. We need to resolve the contact force with impulse-based dynamics, and then we can integrate the force and feedbacks to the haptic device. This is the setup, the framework for these simulators. It includes the bone modeling, includes instruments modeling, the physical simulations, as well as the human-computer interactions. So as I say, the key component is the haptics force rendering calculations. So we have to construct these simultaneous contact schemes to handle the multi-points contacts. And we also take into consideration of the friction force. There's a dynamic or static friction at the contacts. And then we also have to take into consideration of the resistance force. There's a normal force at the contacts. And then through these simultaneous contact schemes, we combine the contact force to generate the corresponding vibrational force from the equipment, and then finally generate the resultant force calculations that can be feedbacks to the haptic feedbacks device. So in order to make sure that our haptic rendering is realistic, we also construct the device for measuring the actual showing force and also measure the actual burning force, and then compare the measured force as well as the simulated force, and we can see that the profile of these two are very similar, and which means that the simulation is in fact quite close to the actual force that the user will experience in the actual procedures. Then to further evaluate the system, we design different test cases, and we invite experts and also invite trainee with very little experience to try on our system. We look at the error measures, we look at the time it takes to complete the procedures, and for these figures, we can see that the experts perform a lot better than the trainees in many different test cases. We can also use our system to perform a virtual surgery, and then we can compare the outcome from the real and the virtual surgery. So the next simulators is about high-fidelity human-computer interactions interface designs for eye surgery. Microsurgery is widely applied in clinics, and it requires high-skilled and long-period trained doctors to complete the surgery. And however, virtual microsurgery training system still lacks haptics feedbacks for spatial perceptions, and also lacks interface for real surgical instruments. So in our work, we employed the VR helmet HTC Vive to display the microsurgical environments. We also designed the conversion device to connect the surgical tools for microsurgery and haptic device. And then another examples in using VR or AR is this holographic augmented reality guidance in AR-guided liver radiofrequency ablations. We all know that tumors commonly are located inside. In this case, it's liver, let's say. Then the doctors cannot directly observe them with the naked eye. And traditionally, we will use 2D imaging or like ultrasound or CT-based guidance to realize really relies heavily on surgeons' experience with long operation times. So in typical radiofrequency operations, the needle have to be inserted into the tumor, and then the high temperature generated from the tip of the needle will then destroy the cancer cells through these treatments. So here in this project, we use HoloLens in the AR guided for liver radiofrequency ablations. So in here, we need to construct the heterogeneous abdominal deformable model. For our initial experiment, we use a phantoms to test our systems. We construct the model, we predict the deformation during the needle insertions, and then realize the dynamic respirations for intraoperative scenes. So that includes this specific dominance anatomy reconstructions, the setting up of this mixed reality guided radiofrequency operations setups, and also to provide visual spatial informations as well as the restorations in intraoperative environments. We have carried out a test to validate the effectiveness of this AR guidance. By using the traditional CD-guided needle insertions, the accuracy is around 8.5 millimeters. And then by using the AR-guided needle insertions, the accuracies can be improved to around 3.23 millimeters. That's quite a significant improvement. Then the next step is that we would like to also consider respiratory motions because the deviation of liver and tumor induced by human respiratory movements is the leading cause of liver biopsy error. So we also apply the HoloLens in the AR guidance for liver biopsy with respiratory motions. In this particular project, then we need to acquire and reconstruct 4D respiratory data. We need to construct the respiratory statistical motion models and also realize the non-rigid respirations for preoperative and intraoperative surgical scenes. And we also carry out experiments, animal experiments for this AI-guided liver biopsy. And we can look at the outcome. Under traditional CT-guided liver biopsy, the error is the accuracy or error is around 16.3 millimeters. However, in the augmented reality guided liver biopsy, it can be improved. I mean, the accuracy can be improved to around 3.43 millimeters. So it is again a significant improvement. So in conclusions, both medical imaging and surgical simulation can play major roles in surgical training and in computer-assisted surgical treatment. Surgical simulation have the potential of becoming a major VR applications. There are still lots of exciting research and developments need to be performed in order to make a truly practical VR-based surgical simulator with very high fidelities. Thank you very much for your attention.